start the recording. All right. So then I think this basically this is a most important principle for this chapter, and this principle also explains some the reactivity trend among the fine details like different esters. Okay, how they are the carbonyl reactivity changed by the ester substitution. That we went through last class. I'm not going to repeat here. And if you you may want to get to the if you're going to take next exam, you may want to write down this sequence of stability of carbonyl groups, okay, at the beginning of your test, just in case, okay. But I would say it's more important for you to justify this sequence of reactivity instead of memorizing. Justify, okay? Justify the sequence. Now, I think we were looking at the nucleophilic acyl substitution in acyl chlorides, okay? Because of acyl chlorides, okay, they are the top one on the reactivity table. So it has a most reactive carbonyl group. So acyl chloride can be converted to any of other carboxylic acid derivatives. Any, okay? Just you have to pay attention to the conditions and the mechanisms. Okay. So let's look at how acyl chloride can be converted to the anhydride. So let's using one particular acyl chloride as example. Just just for the sake of easy writing the structure, let's see, we're just using this guy as the acyl chloride. Okay. So if you want to convert into corresponding anhydride, it has a less reactive carbonyl than acyl chloride. So yes, it's certainly possible to convert into anhydride. Okay, so but you need to provide the nucleophile. So if you look at the structure, see, you need to replace the chloride with the red fragment. Okay, so the nucleophile must contain this red fragment. Okay, so the nucleophile could be provided either in its in the protonated form, means HO. This could be the nucleophile, or you can use its conjugate base. So conjugate base means both are the feasible nucleophile to convert acyl chloride to anhydride. So the reactivity will be different. What's difference between these two guys reactivity wise? Both these this guy or this guy can serve as nucleophile. Which one is more nucleophilic? So this a pair of conjugates, right? A pair of conjugates. You see, if you look at the nucleophilicity, which one is more nucleophilic? Always the negative charge one. Whatever the one has greater negative charge will be more nucleophilic. So obviously the right side one has a whole unit of negative charge, and the left side one is neutral. So the negative charge one will be a lot more nucleophilic. The ballpark number, in terms of nucleophilic reactivity difference is 1,000 to 100,000, 1,000 to 100,000. Okay. So obviously the right side one will be a lot more nucleophilic. Okay, so let's look at the mechanistic aspect of both the reactions. Okay, so if we have this the neutral nucleophile as the carboxylic acid nucleophile, so then let's look at the rate limiting step. So for this kind of reaction, keep in mind when we talk about nuclear rate limiting step, do not assume you always going to have a proton, depending on the reaction condition. Okay. So in this particular case, we know the acyl chloride is electrified. So what is the electrophilic atom here in the acyl chloride? What is the electrophilic atom? So which atom will be electrophilic attacked in the acyl chloride? Electrophilic atom. Oh. Electrophilic atom. So in this acyl chloride is electrified. Whether is the electrophilic atom, that will be a nucleophilic attack. Yes. Carbonyl. Almost always in this chapter, every case always carbonyl carbon, because that's the carbon. The atom has a great amount of positive charge. Then you're looking at this carboxylic acid. Which atom is most nucleophilic? Which atom is the most nucleophilic? We learned in chapter 19 which atom is most nucleophilic. We have two oxygens. Yes, the carbonyl oxygen is most nucleophilic, not the hydroxy oxygen. Okay, because of the if you look at the product after nucleophilic attack, you will know that carbonyl oxygen is the most nucleophilic one. So that will be the rate limiting step. So this will give us so that's nucleophilic, the product of the rate limiting step. And the rate of this reaction depends on what? This just this standard Lewis acid-base reaction, nucleophilic addition. So the rate of this reaction determined by two factors mostly: the electrophilicity of the electrophile, acyl chloride, okay, and the nucleophilicity of the nucleophile. Here the acetic acid, the carboxylic acid. And if you recall the nucleophilicity table you have seen in chapter 6, you probably can find out the carboxylic acid is one of the the weakest nucleophile. We still can classify as a nucleophile. Check chapter 6, that nucleophilicity table. Carboxylic acid is among the weakest nucleophile. We still can use as nucleophile. If you look at even weaker nucleophile like hydrogen sulfate, usually we don't use as nucleophile. Okay, so this is about carboxylic acid about 100 times less nucleophilic than water or alcohol. So this is the rate limiting step. Okay, and this is a tetrahedral intermediate directly formed after nucleophilic, directly after as a product of rate limiting step. And obviously this one can undergo proton transfer. I'm not going to go through the details how the proton transfer happens, because that proton transfer can happen intramolecularly or intermolecularly. So there's a multiple mechanism could be happening. But that effect is, as you know, this is a highly basic. This is alkoxide. This oxygen is highly basic. Okay, and this protonated carbonyl is pretty acidic. So it will give you a undergo a proton transfer, either intermolecularly or intramolecularly, give you the neutral tetrahedral intermediate. And then this neutral tetrahedral intermediate, okay, can undergo, the elimination reaction. So this elimination reaction could be, you know, kind of E2 elimination. Okay, so you have a base. What kind of base will be reasonable in this reaction system? The base could be just a carboxylic, you know, the carboxylic acid itself, you know, or the, you know, another tetrahedral intermediate. So so this base, okay, in such a reaction system, you have to be, this base should be abundant species, one of abundant species in this reaction system. So it could be another tetrahedral intermediate, okay? Say just like this, okay? Could be equal to another tetrahedral intermediate with that OH group as you know, the atom accept the proton, or even the, you know, the carbonyl, you know, carbonyl of the ester as the proton acceptor. So those are the two most common, you know, you know, proton acceptors in this reaction system. But anyway, so this base can take the proton away, okay? And this is, you know, the kind of, say, part of E2 elimination process. And then this proton come to here, then push the chloride away. So that's E2 elimination. And this gives you the, you know, the product. Plus, obviously, HCl eliminated. Okay. So that is if the acetic acid is nucleophile. Okay. Now, if the not acetic acid, carboxylic acid is nucleophile. Now, what if the carboxylate is nucleophile? If carboxylate is nucleophile, then obviously the negative charged oxygen, okay, will be nucleophilically attack the carbonyl carbon. This is the rate limiting step, okay, and you will be getting this alkoxide. Let me just do a partition so that don't be confused. So this is the tetrahedral intermediate, okay? So in this reaction, you don't have anywhere to get the proton because we're not saying this reaction have to be carried out in water or alcohol. So there's no reasonable source for this negative charged tetrahedral intermediate to get the proton. Okay? So that is the tetrahedral intermediate. You will not have a feasible chance for this tetrahedral intermediate to be protonated. So you will just have an ionic tetrahedral intermediate, an ionic one. And then what happened next is very straightforward. So the carbonyl group will want to restore itself, then push the chloride off. And that is what do you call? This is just a standard elimination reaction, and give you the final anhydride. Of course, the chloride also forms. So one common mistake students tends to make is, oh, they always assume tetrahedral intermediate must be neutral. Okay, it does not have to be neutral. You know, the only when there's a reasonable proton source exists in reaction system, then yes, let's say if this reaction is happening in water or happening in alcohol, it's possible for the tetrahedral intermediate, not an ionic tetrahedral intermediate to receive a proton from water or alcohol. But here, who said the reaction must be happening in water or alcohol? And actually, if you use acyl chloride, the reaction cannot take place in water or alcohol because both water and alcohol will react with acyl chloride. Okay, so if you do the reaction of acyl chloride, it's a given that solvent is not water, neither water nor alcohol. Must be something, has no active, no nucleophilic, the fragments like say THF, acetonitrile, DMSO, all those things are going to be fine, but not water or alcohol. Any questions about this one? And if you compare these two rate limiting steps, which one will be faster? The top rate limiting or bottom rate limiting step? Top one, bottom one? You can see these two rate limiters have the same electrophile, okay? Electrophile is same. The only difference nucleophile being different. So whatever nucleophile is more nucleophilic, the rate limiting step will be faster. So the bottom one nucleophile is a negative charge. Top one is neutral. So the bottom one is actually about 100,000 times faster than the top one. About 100,000 times, a lot faster basically. So that bring up to the real consideration if you need to convert acyl chloride to anhydride. So most common way to do it is okay. So if you have acyl chloride, okay, if you want to convert to anhydride, so you will need the carboxylate fragment. So you could provide it, okay, in the form of carboxylic acid, okay, but you can use some at least a catalytic amount of the carboxylate as a catalyst, okay. Why? Because of the carboxylate, okay, is about 100,000 times more nucleophilic than the carboxylic acid itself. Okay. So this catalysis can be considered parallel to the basic catalysis of hydration to aldehydes and ketones. Remember this one? If you have say R2, okay, you react with water, okay, you add OH minus, the hydration will be substantially faster. Recall this? This is basic catalyzed hydration in chapter 8, okay? So why OH minus can be a lot, adding can accelerate reaction because OH minus is about 10,000 times more nucleic than water, okay? So that makes the rate step about maybe like 1,000 times faster, okay? But here, same thing, the carboxylate, okay, is about 100,000 times more nucleophilic than carboxylic acid. So adding carboxylate, yes, will make the reaction faster. Okay? That's just some consideration about such a reaction. Any questions? If you add a small amount of OH minus into this reaction system, serve the same purpose. Just in this anhydride formation, adding small amount of OH minus will serve the same purpose. Why? Because OH minus will react with carboxylic acid, okay, generate a carboxylate, okay. But just for the sake of if you want to make sure, you want to mix small amount of OH minus with carboxylic acid first, okay. So basically, in the carboxylic acid part, you're getting a mixture of carboxylate and the carboxylic acid. Okay? So the real catalyst is carboxylate. Any questions about this? So this is the basic catalysis in this carboxylic, the nucleophilic azo substitution reaction. The key part is we are providing a more nucleophilic nucleophile. This is called basic catalysis. We are providing the conjugated base of the the neutral nucleophile, because the carboxylic acid is a very weak nucleophile. So if we convert to it partially to conjugated base, it becomes about 100,000 times more nucleophilic. So the reaction becomes faster. Like that. Any questions? The next one is if we convert, we want to convert this guy into, say, ester. Okay. So what kind of alcohol we need? We need what kind of nucleophile we need? We need this fragment. Okay. Right? If to do this conversion, we need the RO fragment as a nucleophile. So RO fragment as nucleophile, it can be supplied in two forms commonly: alcohol and alkoxide. Okay, you can guess based on same analysis we have done with the hydride, which was more nucleophilic? The alkoxide. Okay, but practically, speaking, the use of alkoxide could be, less convenient than alcohol, because alkoxide is pretty basic, strong base. Okay, so we often just, for the sake of easy handling, often neutral alcohol is preferred. Okay, neutral alcohol is preferred. Okay? So then if we again, we can look at the mechanism of the neutral alcohol react with acyl chloride, and the alkoxide with acyl chloride. So let's look at alkoxide. If alkoxide does react with acyl chloride, and then so it's pretty straightforward. This one attacks. This is rate limiting step, okay? But the thing is that this rate limiting step, although is rate limiting, but is actually really fast, because alkoxide is highly nucleophilic, and acyl chloride itself also very electrophilic. So this reaction is usually, it's so fast. As long as those two kind of molecules get contact with each other, we immediately react. Okay, so then this is a rate limiting step, and then the second step just undergo elimination to restore the carbonyl group. So that is a restoration of a carbonyl group is a driving force. So this reaction is really fast, but as I said, the alkoxide, handling may not be easiest thing to do. Okay, so we often use neutral alcohol. If it's neutral alcohol, then basically you have this so this slow step is about 10,000 times slower, okay, than the anionic version. And then you have a proton transfer step. Again, it could be, the proton transfer could be intramolecular or intermolecular. So I'm not going to write all the possibilities, but just say a proton. This usually is not rate limiting, usually. This is tetrahedral intermediate. Then the the tetrahedral intermediate, okay, can undergo base assist, the elimination. So you can consider this is a version of E2 elimination. So you can treat this carbon with alpha carbon, and oxygen is beta atom. So this will give you the ester product. So the because of the lower rate limiting step, where you have neutral alcohol react with acyl chloride, the alcohol is a weak nucleophile. So this rate limiting step actually could be really affecting your reaction rate. So sometimes at the room temperature, it could take more than hours to complete the reaction. So obviously one way to catalyze such a reaction is that just we utilize the standard, just if we borrow the concept of basic hydrolysis. So how do we enhance how do we speed up this reaction? If we borrow the concept of basic hydrolysis, so how do we speed up this reaction? We could add, okay, in the alcohol, we could add, the small amount of alkoxide, okay? If we add a small amount of alkoxide, and that reaction can be dramatically speed up, because alkoxide, as we know, is about 10,000 times more nucleophilic than alcohol. Okay? So this will help, the reaction become faster. But alkoxide, as I said, it's highly basic and also very hygroscopic. So handling may not be easiest. So most of when we really carry out such a reaction between acyl chloride and alcohol, we often using different way to speed up the reaction. So the other way is we adding this compound, pyridine, okay, can often speed up the reaction between the ester and the acyl chloride. Okay, why pyridine can speed up a reaction? The first thing for pyridine to be able to speed up a reaction required is because the pyridine is much more nucleophilic than alcohol. Because pyridine has a nucleophilic nitrogen atom. We know nitrogen atom being less electronegative than oxygen. So its lone pair will be, it's more willing to give out a lone pair. So that makes a nitrogen atom, if it has a valuable lone pair, it's typically much more nucleophilic than the corresponding species with oxygen lone pair. Okay? So the overall the usually if you measure nucleophilicity of pyridine is about 100 times to 1,000 times, okay, more nucleophilic, okay, than OH, alcohol. Okay, so as a result, okay, if you have you have both pyridine, alcohol, and acyl chloride. Which nucleophile going to react with acyl chloride faster? The pyridine, because about 100,000 more nucleophilic. So now this reaction gonna be faster, okay? Let's say we call it K1, okay? And this reaction, let's say called K2, okay? K2 is greater than K1, okay? So this rate constant, K2 is greater than K1. This is a first requirement. K2 is much greater than K1. But this nucleophilic attack give you what? Just you can look at it. we will have this is tetrahedral intermediate, okay? And then this tetrahedral intermediate will, what will happen with tetrahedral intermediate? We have done a few times already. What is next? What will be happen next on this tetrahedral intermediate? Huh? Yeah, the key part is look at the driving force is carbonyl group is a really strong double bond. Okay, they want to take every opportunity to restore itself. Once it's it's destroyed, they will take every opportunity to restore itself, as long as doing so will not create a horrible leaving group. Okay, so here the chloride is pretty good leaving group, so no problem. So the carbonyl group will take every opportunity to restore itself by pushing a chloride off. This will give you the this one. Okay, so basically from here to here, is this a nucleophilic acyl substitution reaction? From here, okay, to here, is that nucleophilic acyl substitution reaction? Yes or no? From here to here, is that nucleophilic acyl substitution reaction? Yes or no? You have nucleophile, okay? Here you have the nucleophile pyridine replace chloride, all right? It has a nucleophilic acyl substitution reaction, okay? So that's a nucleophilic acyl substitution reaction using pyridine to replace chloride, okay? Now you look at this guy. This guy. This is a very important, you know, we call active intermediate, okay? Because analyze this structure, you can understand why pyridine can speed up, you know, quite a few. The use of pyridine can speed up quite a few nucleophilic acyl substitution reactions. Because when you add a pyridine to a nucleophilic acyl substitution reaction, you have the potential to form this one, okay? And look at this one. You think this guy has a more electrophilic carbonyl than the acyl chloride, or less electrophilic carbonyl than acyl chloride? So let's say, if you look at this red one, okay, carbonyl, and the blue carbonyl, which one is more electrophilic? Electrophilic. Which carbonyl is more reactive, more electrophilic? The red one. Why red one is more electrophilic?
Due to the charges, chlorine puts the negative charge away from the carbonyl, but the nitrogen does not pull that much.
Okay, so the things here, okay, with the major argument we say why chlorine, okay, is so bad at stabilizing carbonyls because of carbon-chlorine bonds are long, right? But that means chlorine still can donate a bit electron to carbonyl, although it's weak, not good at it, okay? Because chlorine still have long pairs, right? It's not that great at it, but it can do something. Give an electron to the carbonyl. But do you think that the nitrogen in the in the compound in the green frame, do you think that nitrogen that bound to the carbonyl has any capacity to give electron to the carbonyl? Any? Do you think that nitrogen has any capacity to give the electron to the carbonyl? It's absolutely zero. Okay? Because it has no long pair on here, and it's a positive charge. It is positive. positive charge. You can't really take something already positive charge. So just like if I'm already owing, let's say, $10,000, you can't really ask me to donate, money. I owe that much money. You want me to donate this? Really, I can't do it. Okay. So that's just something here. The nitrogen already is lacking electrons being positive charge. Okay. So we can't donate any electron to the carbonyl. So that makes the carbonyl in this carbonyl in this guy, the blue carbonyl is even more electron deficient than the red carbonyl. That means the blue carbonyl is more electrophilic than the red carbonyl, because this nitrogen has zero capability to offer electron to the carbonyl. Actually, this nitrogen probably will steal some electron density from the carbon, because being positive charge. So that is why this guy, okay, will be more reactive, more electrophilic than acyl chloride. Okay. So because of this reason, this reaction from here to here is not thermodynamically preferred, because the carbonyl is less stable. Okay. But nevertheless, you can form like a few percent, okay, of this one, a few percent of this, because of chemists has done spectroscopic study. They identified, indeed, they have a small amount of this, the called active intermediate, okay, activated intermediate form in the reaction. Chemists use spectroscopy. They studied, okay, they detect small amount of this guy indeed form in the reaction. Let's say between acyl chloride and alcohol that is catalyzed by pyridine. They detect it, okay, small amount this indeed they can detect this, okay. And this one is more electrophilic than the acyl chloride, okay. So then what happens next, you can understand, because this one's more electrophilic, so then the alcohol can react with the this one faster. What alcohol we use? Just R. We call it R star. Okay, I can erase it. What? So if you have the alcohol, okay, you can react with this one faster than the than with acyl chloride. So this will be, let's call K3. So this K3 also is larger than K1. K3 also larger than K1. Okay. So because of this reason, you convert a slower rate limiting step, this one, okay, a slower rate limiting step to two faster, the steps. Both reactions going to be, so these two steps, both going to be faster than this reaction, okay? So then overall reaction is substantially faster. Okay? So that is why adding pyridine, can speed up a reaction. And here the pyridine mainly serve the role of called nucleophilic catalyst. Nucleophilic catalyst. Okay. So this is a little different from the basic catalysis. A basic catalysis is adding a base, convert the nucleophile to its conjugate base. And the natural is more nucleophilic than the neutral nucleophile. Okay, but here is the nucleophilic catalyst will be attacking the electrophile faster. Okay, and such attack generate a new electrophile is more electrophilic than its original electrophile. So if then the new electrophile can react with the original nucleophile faster than the original electrophile does. Okay, so that could give you a faster reaction. That is how adding purity can speed up reaction between acyl chloride and the alcohol. Okay. Any questions about this? So this is one is in the practice exam for those of you who took a look at the exam. Okay. So this is a key principle. Explains why pyridine can speed up, catalyze the reaction of the alcohol and the acyl chloride. Any questions?
Basically, the nucleophilic catalyst because it makes electrophile more electrophilic.
Yeah, nucleophilic catalyst first will be more nucleophilic than your main nucleophile. So that nucleophilic catalyst will react with the electrophile faster. Okay. That's the first requirement. Okay. The second requirement is your nucleophilic catalyst will react with your main electrophile, generate a new electrophile that is more electrophilic than your main electrophile. So if you look at this reaction is, so if you look at the reaction, this is your main electrophile, right? Main electrophile, okay? This is main electrophile. And this one is your main, let's say, just using the easy one, this main electrophile, okay? This is a main nucleophile, okay? And then the pyridine is your nucleophilic catalyst, okay? So because of pyridine is more nucleophilic than your main nucleophile, so pyridine reacts with your main electrophile faster, okay? And we don't think about exact mechanistic. So this reaction so this reaction is faster than your main reaction. We look at the detailed mechanism, explain why it's so, but just from reasonable, if you just using a more concise version, look at the reasonings, okay? So because of the nucleophile, main nucleophile, nucleophilic catalyst pyridine is a lot more nucleophilic than this. So this reaction is faster than second reaction. Okay. Then because of the this one, okay, is more electrophilic than acyl chloride. As I spent quite a bit of time to make the argument. Okay, more electrophilic. More reactive electrophile. Okay, then this react with alcohol. this reaction also is faster than the reaction 3. So both reaction 1, okay, and the reaction 3 are faster than reaction 2. Reaction 2 is the uncatalyzed reaction, okay? Then adding the period, you have reaction 2 become reaction 1 and reaction 3 combination. And both reaction 1 and reaction 3 are faster than reaction 2. So overall reaction becomes faster. Okay? So basically, the nucleophilic catalyst must be more nucleophilic than your main nucleophile, and the nucleophilic catalyst must react with your electrophile, generate more electrophilic electrophile. So it can react with main nucleophile faster than the original electrophile does. Yes?
What will you say, like 3 is more reactive than 1?
No, both 1 and 3 are more reactive, are faster than reaction 2.
No,
Both.
Can we compare 3 and 1 with each other?
3 and 1 you can't, because of you have different nucleophile and different electrophile. Both nucleophile and electrophile are different. How are you going to compare, right? It's difficult to compare, because we say 1 you have better nucleophile, okay? 3 has better electrophile, so it's hard to compare, right? But it's easy to compare 1 and 2. They share same electrophile, so the better nucleophile lead to faster reaction. And the 2 and the 3 also can compare. They share the same nucleophile. So better electrophile make it faster. You can't compare 1 and 3. I don't know 1 and 3 which one's faster. Okay? You see the logic here? I'm not asking you to make compare based on memorization, but based on logic. Okay? All right, so that is acyl chloride react with the convert to ester. Now let's say if acyl chloride convert to amide. So you will need, in order for you to do this conversion, you will need this fragment, okay? So this fragment, again, you could provide the neutral version called amine, or you can use its anionic version called amide, okay? Almost nobody using the amide. Why? Because amide is so basic. It's 20 orders more basic than alkoxide or hydroxide ion. It's actually very challenging to use that. It's not saying impossible, but very challenging to use that. So pretty much always we use neutral amine, okay? And besides neutral amine, again, I hope you check that nucleophilicity table in chapter 6, organic 1. It's about 1,000 times more nucleophilic than alcohols and the water. Okay, so usually it's reactive enough. So you don't need any catalysis. I mean, if you meet acyl chloride, they will immediately react. They will react on contact. Okay, so you don't need any catalysis. Just the contact, they will react, because this guy nucleophilicity is about 1,000 times greater than water and alcohol. Why? Because nitrogen is sizably less electronegative than oxygen. So nitrogen atom is a lot better, provides lone pair. Okay, so that's why this just directly react. No catalysis ever needed. Okay, you don't ever need it. Okay, so you can directly mix these two guys. Okay, then if you look at the rate limiting step, okay, just this. Oh, scary. So this rate limiting step is just but because you have the hydrogen here, okay, so this is a slow step, but this slow step usually pretty fast compared to other rate limiting steps. Then you have a proton transfer, become neutral tetrahedral intermediate. And then, you know, the just have a base here, kind of E2 elimination, okay, give you the amide. But if you look at this overall reaction, it forms hydrogen chloride. Okay, so I hope you know amines, they are highly basic. So this HCl will react with the amine. So HCl will react with amine. And then become protonated amine. And the chloride ion. Okay. So if you don't add a base, okay, you basically what you'll be seeing, you if you in order to in order to convert acyl chloride into its corresponding amide, you need 2 molar equivalent of the amine, because 1 molar equivalent of amine is needed to convert to amide. Okay, the other molar equivalent of amine is needed to neutralize the formed, hydrogen chloride. So that's the reaction if you just add the amine. So you become this. This is going to be a reaction. So is this something you would like to do? In practical purpose, not, because amines are not so cheap. So you don't want to waste the amine to waste 1 molar equivalent of amine to neutralize HCl. So often what you do is instead of spend the extra mole of amine to neutralize the formed hydrochloric acid, you can add 1 molar equivalent of hydroxide ion. This could be sodium hydroxide or potassium hydroxide. They are substantially cheaper than amines. So in this case, so you can get the the amide product and the chloride ion. And obviously water. Okay, so this is really the typically do in the lab, because this reaction gonna form HCl and consume 1 mole of amine. You don't want it to happen. Amine is expensive. So add 1 mole of sodium hydroxide. Okay, so sodium hydroxide is not a catalyst. It's just to remove the the formed HCl, so that you don't have to use that much of amine. Huh? If you don't neutralize it, you will need 2 molar equivalent of amine. Oh, okay. Because let's say if the amine, let's say if you just using 1 molar equivalent, right? So the only half molar equivalent of amine will be converted to amide. Why? Because that half molar equivalent of amine reactively will create a half molar equivalent of HCl, and the HCl will protonate the other half mole of amine. And then amine loses the ability to be a nucleophile. So after amine is protonated, it has no lone pair, and then it is incapable to act as a nucleophile. So that's why you need either 2 molar equivalent of amine, or you need hydrogen hydroxide to kind of. You can also consider the hydroxide is to deprotonate the protonated amine to release the free amine to act as nucleophile. Either way, you can think about it. Any other questions about this amine amide conversion? Acyl chloride amide conversion? So then that's all the conversion from acyl chloride to conventional formal members of carboxylic acid derivatives. So what about the carboxylic acid? Okay. If you want to convert carboxylic acid, okay, obviously you need to introduce OH, right? OH replace Cl. So you can use just H2O to do that, or OH minus to do that. Okay. So you might think, okay, based on the same analysis we have done so far, okay, both will work, and OH minus is just about 10,000 times faster than H2O. Okay, but the story will be a little complicated. Okay, so let's look at the what happens if you do the OH. Let's say first H2O. If it's H2O, so the rate limiting step is like here. So that is a rate limiting step. That's a slow step, okay? Then you can have that, the proton transfer. Again, because it's have a multiple possibilities, so I'm not gonna, the exhaust all the possibilities. Become this tetrahedron intermediate, then you may have the base, typically just water. Take that proton away, okay? So give you this kind of E2 elimination, give you the carboxylic acid and HCl. So that is when water react with acyl chloride, okay? And then now, what about the hydroxide ion? So that is a slow step. Then this slow step will involve the undergo restoration of carbonyl group. Okay, but that thing is the complication here. Okay, in this kind of nucleophilic acyl substitution reaction, do not forget about the acid-base reaction can always get involved. And as we know, carboxylic acid is fairly acidic, okay? So what happens here is that if the reaction happens in a basic environment, you have a basic environment means you always have the sufficient supply of hydroxide ion. So what happens next? The hydroxide ion will take that proton away. So give you this is acid-base reaction with very high equilibrium constant. Generally, it's about 10 to the 11th order. So that acid-base reaction, hydroxide ion, they react with the carboxylic acid. And that will always happen in a basic environment. So that effect, if you're using you treat acyl chloride in a basic environment, you will direct get a carboxylic ion. You will not get the carboxylic acid itself. You will direct that you will end up getting carboxylic ion. And such proton transport is, the highly thermodynamically favored. So you will always get this, okay? But if you look at these two rate limiting steps, okay, so obviously the lower rate limiting step is about 100,000 times faster than the top rate limiting step. Okay? So look at overall result is if we have a acyl chloride react with water in a neutral environment, okay, you will get a carboxylic acid. Obviously, you will get HCl as well. If you maintain the, mass balance, okay. Now, if you do the same reaction in a basic environment, OH minus, you will get a carboxylate as a product. You will get a carboxylate as a product, okay? Any questions? So actually 2, and you get some water, okay, if you really want to balance, okay. So this is everything about, the nucleophilic acyl substitution reaction of acyl chlorides, okay. So really, what you can see is acyl chlorides can be converted to any other carboxylic acid derivative as long as the proper nucleophile is supplied. Okay? And we talk about the basic catalysis in this section and the nucleophilic catalysis in this section. Okay? Those are two different concepts. Nucleophilic catalysis means you are using a more powerful nucleophile than your main nucleophile. Basic catalysis means you're adding a base that converts your main nucleophile to its conjugate base. It's two different concepts. Okay? Any questions? If not, let's have a 5-minute break.